This is exam 1, essay 2 question. This video is about resting membrane potential, action potential, and some other factors that affect those two things. So just to explain resting membrane potential really quickly. Resting membrane potential is the electrical potential established by the membrane. So in a cell, naturally because of chemical gradients, there is established electrical charge around the membrane. So the inside of the membrane is slightly negative and the outside of the membrane is slightly positive. When we refer to this as resting membrane potential. So that is what the cell's potential, electrical potential is at, measured in millivolts. Naturally, when the cell isn't doing anything. And that'll change as we talk about action potential. Action potential is when a signal is sent through the cell, and when that occurs, the resting membrane potential, well, I guess there are two different things. The resting membrane potential is the same, and then the action potential is when it moves away from that. But some properties or characteristics of the cell that allow this to happen. One thing, the membrane is semi-permeable. So what this means is the membrane is permeable to some things, and other things it's impermeable to. And there are kind of three things or three channels that kind of regulate this pretty heavily, or main ones. And they'll have to deal with the ion concentration. So the first one we're going to talk about, this is the sodium-potassium pump. So the sodium-potassium pump pumps out 3 sodiums, pumps in 2 potassiums for every 1 ATP. From the first essay video, we talked about active versus passive types of diffusion. And this is an active form of diffusion, right? It uses ATP, it's primary active. And this is one of the first and main things that causes there to be an electrochemical gradient along the membrane. And the reason for that is if we're pumping out 3 sodiums and pumping in 2 potassiums, we're pumping in less positive ions than positive ions that leave. So therefore, this pump works, right? More sodium leaves, more potassium comes in. It leaves the membrane slightly negative, right? Because more positives are going out than coming in. But then there are 2 other pumps I want to talk about, or I guess they're not pumps, or channels that affect this. So the first one, this is called our sodium voltage gated channel. It has 2 activation gates, an activation gate and an inactivation gate. And then one other is our potassium voltage gates, and I forgot there's one more, and that is potassium leak channels. So in this example here, these channels help establish a gradient. So naturally the cell allows some things inside, it pushes some things outside, and the cell, in order to function properly, regulates those concentrations of ions. So inside the cell we have a high amount of potassium, right? Potassium is being pumped in. Outside the cell, we have a high amount of sodium. Inside the cell, low amount of sodium. Outside the cell, we also have a high amount of calcium, as well as a high amount of chloride ions. And so, naturally, all of these, the chemical gradient pulls them in. But because the cell is non-permeable to them at the resting membrane potential, they don't come into the cell. However, the potassium leak channels never close. So the high amount of potassium inside the cell leads to a chemical gradient pulling it outside the cell. So what happens here is potassium will leave through this channel, and as positives leave, the inside of the membrane becomes more negative. The outside becomes more positive. As this occurs, there's not only just a chemical gradient now, there's also an electrical gradient that pushes it back the same way, right? This positive charge is going to be attracted to these negative charge and repelled by these positive charge. So as the concentration gradient changes and the electrical gradient changes, we reach a level of equilibrium where the force from the electrical pull or push and the force from the chemical gradient is equal. That's where we reach resting membrane potential. Um, so potassium is our biggest contributor to that resting membrane potential, and it's our greatest factor. So some of the things are going to contribute to the resting membrane potential's magnitude or its size, right? So let's just pretend this is a neuron, right? It's going to be at negative 70 millivolts. Here's our resting membrane potential. Some cells are higher or lower. Most cells that have action potentials are somewhere around negative 60 to negative 80, but there are some cells that don't see action potentials or spikes in their electrical potential, and so those ones have around a negative 5 or negative 10 resting membrane potential. But that's not important. They're arbitrary numbers mostly to us, but what this means is this is where the membrane sits naturally. The inside of the membrane is naturally negative. So there's some factors. We'll talk about factors for these three things. The two main factors that contribute to resting membrane potential are permeability as well as our concentrations. So sodium concentration, potassium concentration, calcium concentration, and then our permeability to sodium, potassium, calcium, and chloride. So we're just going to use a couple of words to describe what's going to happen with these, right? So changing the concentration, for example, if somebody is what we refer to as hypernatremia, that means they have an excess amount of sodium extracellularly. So extracellular sodium increases. So if we use the cells as our example, right? Outside we have 150, inside we have 10. They're arbitrary numbers, but I'm just trying to use to show you the chemical gradient, right? That's pulling the sodiums in. Well, if we change the 150 to 160, for example, there's going to be a greater pull to have them come in. However, our sodium gated voltage channel is closed. And because it's closed, it's not going to change the resting membrane potential. This will have an effect on the action potential, which we'll bring up again later. That can affect the action potential, but not the resting membrane potential, at least at this situation. So let's use potassium as an example. Instead of saying let's say we have hypokalemia. This means there's a decrease in extracellular potassium. So let's say we have 100 inside and 10 outside. We're going from 10 to 5. We're decreasing. That's going to increase this gradient, right? So more potassium ions are going to flow out. As more potassium ions flow out, that will lower our resting membrane potential. Same thing if it was hyperkalemia, the decrease in the gradient, right? If this became, instead of 5, now we have 15, right? They're going to move out slower. It would make it more positive, or et cetera, et cetera. Now, I want to talk about calcium real quick because it will affect, actually, we'll talk about calcium when we get down to action potential because it's more effective with the action potential than the resting membrane potential. But now let's just talk about permeability. If for some reason the membrane becomes more permeable to any of these ions, it will change what happens, right? It becomes more permeable to potassium. That's basically saying we increase the amount of potassium leak channels, more potassium is going to leave, right? If more potassium leaves, it's going to become more negative. If it becomes less permeable to potassium, like if a drug blocks some of the potassium leak channels, that is going to increase the resting membrane potential. Now we use a couple of words to talk about this. If it moves above, we call it depolarize. If it goes below, we call it hyperpolarize. And then one more word, if it goes from D and then it returns back to normal, we call it repolarize. And so it's the same with all these ions, right? It just depends on the chemical gradient. If all of a sudden the sodium becomes permeable to to calcium, the calcium will move inside the cell, right? Following its gradient, it will change the inside of the cell to become more positive. This can actually be a cause of action potential. So could any of these things. And we'll get to action potential in a minute. But before we get there, I just want to talk first about, now that we've covered these factors that affect the resting membrane potential and will affect the action potential as well, I wanted to talk about two principles. One is called the Nernst equation, and then the other is called the driving force. So let me draw another graph here. So the Nernst equation is E is equal to negative 61.5 over Z times the log of concentration in over concentration out. So what this equation is saying is the electric potential of a cell should be based on one ion alone, negative 61.5 divided by the atomic number of whatever the ion is, right, times the log of the concentration inside divided by the concentration of the outside. And so what this is saying is an experiment, if we have a semi-permeable membrane, we have one ion, right? So let's say we have some potassium chloride here, and it's only permeable to potassium. Some potassium is going to move over, right, as we talked about the chemical gradient, but then we'll also get the electrical gradient and eventually reach equilibrium. If we put in a voltmeter, the Nernst equation could calculate what the difference in electrical charge is. However, the Nernst equation does not work perfectly in predicting what happens in a cell, because in cells, inside the cell, there are more than just one type of ion affecting everything, right? So Nernst only works perfectly in experiment. So if this is our normal cell, right, we have our negative 70 millivolts. What happens is if we did the Nernst equation for just potassium, we should get something around negative 95 millivolts. Well, if we do the same thing for sodium, we should get somewhere around 55 millivolts. Those are very different. But what the Nernst equation does help us understand is driving force. So driving force is the principle that the more force pulling on one ion, the greater chance that ion will have on affecting the cell. So the driving force is equal to whatever the voltage of the membrane is. So in our example, that would be our negative 70 millivolts, and then minus the Nernst potential, which should be the lowercase e. So whatever the Nernst is, that subtracted from the normal amount will tell us the driving force. So just to show the driving force graphically, here's our driving force for sodium. Here's our driving force for potassium, right? If we do negative 70 minus negative 95, we get positive 15. But if we do negative 70 minus 55, we get negative 125. Oh, sorry, this is 25 plus 25, and negative 125. I believe I did my math right. Whatever, it doesn't matter. The purpose is to show you that the driving force for sodium has a far greater magnitude than the driving force for potassium. And this is what causes our action potential. So an action potential is when we cross something known as the threshold. So I'm going to draw another graph here. We have our resting membrane potential at negative 70 millivolts. Then we have something called a threshold. So if you remember before, we talked about a cell. We talked about all these different channels. The potassium leak channels always work, but we talked about two channels that don't always run, and they are voltage-gated sodium channels and voltage-gated potassium channels. These two types of channels only open if there's a change in voltage. And so that voltage is known as the threshold. The threshold is when these channels will start to open. So an external stimulus, for example, we talked about concentrations, right? And then we talked about permeability. So let's say all of a sudden the cell becomes permeable to calcium. For some reason, a calcium channel opens up. Well, now calcium is racing inside the cell, and now this previously negative cell is going to be depolarized, right? So it's going to cause it to go up. Well, if that depolarization is strong enough, it is going to cause what is referred to as an action potential. Sorry, my hands are so shaky. So this one here, that's a resting membrane potential. 2, this is where we receive the stimulus. That's when the calcium plus channel opens and allows calcium to come inside. It then causes the negative 70 to become more positive, right? Because positive's coming in, increases. This is referred to as a graded potential. So a graded potential is any change in the resting membrane potential towards the threshold that doesn't reach the threshold. So anything before the threshold is referred to as a graded potential. So for example, if not enough calcium comes in the cell to cause it to cross the threshold, then we would see it as just a bump. And that would just be referred to as a graded potential. Sometimes multiple graded potentials will come and through repeated stimuli reach our action potential. So here in our action potential, we have what is referred to as the rising phase, the falling phase, and then the hyperpolarization phase. So here, so just to talk about each one of these, what's happening here is at 3, right here, when we cross the threshold at 3, what's going to happen is this sodium channel is going to open. Sodium is going to flow in the cell. That's going to cause a spike. It's going to push towards the Nernst potential that we calculated earlier, right? It's going to move towards that. The potassium channels are also going to start opening at 3. What happens though is when this channel opens pretty quickly, this inactivation gate comes down. So each one of these has an activation inactivation gate. This is almost like a ball and chain. It comes in and plugs it like a tub almost. And so this will open and this will close. So from 3 to 5, these are opening, open. All of them are open at 3, and then they're slowly closing by the time we get to 5. So at 5, all of these sodium channels, for the most part, these voltage gated sodium channels are closed. But all these potassium channels, they're slower than the sodium channels, so they take a while longer to open. They open slower, causing the stop as well. And by 5, they're all open. As we repolarize at 6 in the falling phase, these sodium channels are releasing sodium, right? Releasing positives, causing it to return down towards the resting membrane potential. However, by the time they close, the cell actually hyperpolarizes a little and then returns to our resting membrane potential here at 8. So the reason that this causes such a steep downturn is, remember those leak channels? The leak channels are always moving out. But all of a sudden when we open our potassium channels, we're increasing its permeability, right? Now we have twice as many channels open, and so changing the permeability will change the flow. More are gonna flow out. That's gonna decrease it or cause it to repolarize. So those are all the main factors of what's going to affect the action potential. And as we said earlier, I just want to come up and bring it back. Concentration can also affect the action potential, and I just want to talk about this real fast. Calcium, now sodium, and potassium can also affect the action potential, and they can cause, for example, if we have an increased amount of sodium, we have hypernatremia, natremia outside the cell. That's going to cause this part of the graph to be steeper here, because the concentration gradient will be more when the voltage gated channel opens here at the threshold. More is going to come in faster. But I wanted to talk about sodium, so let's just say we have a membrane here, and here is our good friend, our sodium voltage gated channel. So what's going to happen here, right? The voltage changes, and it opens. The reason it opens is next to this activation gate we have what we refer to as the springy thingy. It's a helix that goes through a membrane of proteins that bond to calcium ions. So the outside of the cell is positive, right? And the inside's negative. So when the cell is at rest, these negative charges will attract the calciums and pull this down. These pluses will repel it and push it in. And so it's at rest. However, when these change, the springing finger will move up, it will open this gate, sodium will flow through, and then this gate will close. But if we change the amount of calcium, right, we change concentration of calcium, let's say we decrease, we have hypocalcemia. So if we decrease the calcium outside, that means less calciums are going to bind here. So let's just get rid of this calcium, right? Now we only have 2 instead of 3. Well, now since we only have 2, the positive charges are only repelling it less, and the negative charges are attracting it less. So it's more likely to move outward. And so this increases the sensitivity. But instead of changing the resting membrane potential in this example, it's going to decrease the threshold. Now the threshold is greater, or is lower, right? Closer to our resting membrane potential. It can even lower all the way to the resting membrane potential in certain situations. And what this is going to happen is a smaller stimulus, a smaller graded potential is necessary to cause an action potential. This can cause lots of problems, but it also can be very helpful in certain situations. Okay, now we've covered action potential and different concentrations. And we've talked about all the ions currently involved and all the different parts, right? As we said here, we're at a normal level. 2, something happens, the permeability or concentration changes, or the cell can also receive stimulus from another like neurotransmitter, right? At 3, we pass the threshold, and the sodium and potassium channels are opening. By 5, all the sodium ones are closed, and the potassium ones are just finishing opening. By 7, they're all closing. We return back to 8 throughout that. So all of these channels, the leak channels, the voltage gauge, sodium and potassium channels, are super important here. Just to note, we always have the sodium potassium pump here. It is always pumping in and out sodiums and potassiums. Your body is always, every cell is always doing it. It's one of the biggest metabolic processes in our bodies. So just to cover once again the difference between graded potential and action potential. Action potential goes above the threshold, graded potential is beneath the threshold. And a graded potential can come from the same stimuli that an action potential comes from. It just depends on its magnitude if it crosses the threshold or not. So now we're going to talk a little more about neurotransmission a little more, specifically with neurons. So we have, let's just say we have a neuron here. So we got our dendrites, we got our axon, and then, or we have our soma, and then we have our axon and our axon terminal. And so if your brain says muscles move, your neuron's going to go all the way down to this muscle and release a neurotransmitter that causes your muscle to move. But this is super important about action potential because this cell isn't circular, right? We're going to get a graded potential in these dendrites, which is going to move through the soma. And if it reaches here, called the axon hallux, there's lots of sodium voltage gated potassium channels. If they cross the threshold, it causes an action potential here. And that action potential causes a chain reaction down the axon. If it's strong enough to go all the way to the axon terminal, release those neurotransmitters, and move the muscle, right? Yeah. Anyways, so there are a couple of factors that affect these neurons, and a couple of terms we use. Capacitance is one, and then the length constant is the other. So in lecture, we called these perpetuations of the action potential bongs, or almost like a sound wave, right? And so capacitance, there's two ways to write this. We can write Q over V, or we can write epsilon times A over D. Oh, that's a D. So Q is charge and V is voltage. So capacitance is the measuring of what charge we get per volt. So how much charge has to be separated to get our voltage? And that's the best way to define it, but this equation is also helpful. Epsilon is permeability, A is area of the charge, and then D is the distance between charges. So in our example here, right, the area of these charges is however big, we'll just say it's constant, but then D, the distance, they're really close, right? All that's there is that membrane, so this will be bigger, and then the permeability. So that capacitance will measure how much charge is necessary to get the specific voltage we have. So it's kind of like the efficiency. If capacitance is low, or less charge is needed for the same voltage. And this has a big effect when we talk about myelin in a minute. But let's just move on to length constant. Length constant is represented by lambda is equal to the square root of Rm over Ri. So Rm is the membrane resistance, and Ri is the internal resistance. So inside the cell, there are proteins that are negatively charged, and since this action potential, right, is a positive charge spike up into the positives, if there are lots of negatively charged inside the cell, right, these negative charges are part of the membrane, as well as some proteins that are negatively charged, it can stop the action potential from perpetuating. This can also be affected by the diameter as well, right? A smaller diameter is going to have more resistance than a larger diameter because there's more space for the signal to move through. And that also affects this internal resistance, but then the membrane resistance is also this charge, right? If things are trying to come in or out of the cell, this charge can repel them and make it so the action potential isn't as strong downstream. And so this will shorten the length constant. But the length constant, what's important about it is length constant is how far the signal is perpetuated, right? When we have an action potential, if we want our muscle to move, we want that signal perpetuated all the way down the axon to the muscle so that we move. However, if the length constant is too small, or the capacitance is too big, or tons of other factors, the action potential will not reach the end of the axon. The axon terminal will not signal the muscle. So this is all very important. So in our body, our cell uses what is known as myelin. So I'm going to draw another dendrite here, or well, I guess these are dendrites. I'm going to draw another neuron. There's axon terminal here, right? Dendrite, soma, axon, etc. So we have what is known as myelin sheath. It's gonna come around. Inside the brain and central nervous system, these are done by oligosaccharides, and then inside the body, these are done by Schwann cells. So myelin does a couple of things. One, it's faster. Communication is faster because of it, and we're going to talk about why that is. So first, let's talk about the length constant. We'll return to capacitance. Myelin decreases internal resistance. The way it does that is it affects capacitance. So if we have a bare cell, we'll just draw the axon part of the cell. No myelin, we have all these pluses and all these minuses. Well, myelin decreases capacitance, so when there's myelin, less negatives are needed to get the same voltage. So because of that, internal resistance goes down. There's less negative charges inside the cell, right, that are going to try and stop the action potential. So that decreases internal resistance, and then it increases membrane resistance, because these few charges that are out here have a greater effect on the potassiums that want to leave. And I'll get to that more in a minute as we talk about capacitance. So an increase in this, a decrease in that makes our lambda bigger. So the length constant increases every time. We'll represent that with the lambda. Right, length constant increases. So that means if we have myelin on a sheath, it's going to be easier for it to reach the end and communicate with the next cell. So then with capacitance, what's happening here is if we talk about permeability, it decreases permeability. The sheath covers this part of the cell, so nothing is going to get through there. So then we only have these pockets where things can go in and out. Because of that, permeability decreases. Well, what also happens is the distance between charges here is greater than that in a cell without myelin. So D increases. If you do all that together, right, decrease here, increase here, capacitance is smaller. Capacitance is going to decrease. And once again, the reason for that is because there are these less charges necessary, right? Capacitance is lower, less charges are necessary to maintain the same voltage, and they're separated more. These charges will have a greater effect on our potassium link channels as well as all of our other channels. So what myelin will help do is, as we get a sodium channel, right, sodium voltage gate channel, it opens, it's going to cause all these positives here. It will then perpetuate down better through the cell to pass along the signal. So that's how myelin affects the cell, and this is super important because it's how our brains and body work at a speed that it does. We're not super slow. So overall, I believe that's everything for resting membrane potential as well as action potential, right? We talked about the properties and characteristics that affect the resting membrane potential, the permeability and the concentration. We talked about conditions that make the resting membrane potential higher, right? Once again, those same things, those the semi-permeability of the membrane, but if that permeability or that concentration changes, it will change the magnitude of the resting membrane potential. We talked about the Nernst equation and the driving force. And then we talked about the characteristics of an action potential, what happens in each phase, what's happening with all the different channels, and the ions. And just one thing I forgot to talk about before we end here, in an action potential, I forgot to talk about two important terms. We're going to call them our relative refractory period and our absolute refractory period. So refractory period, what it's saying is another stimulus cannot cause another action potential. So what's happening in the cell, right? Multiple graded potentials or multiple signals are going to come to cause multiple action potentials to perpetuate the signal. But these two terms, the refractory periods, limit that. So refractory period is how soon can the cell send out another action potential again. So we have two. We call this first one the absolute refractory period. And that means no matter what, no matter how strong the stimulus, another action period cannot be caused. And the reason for that is because this is literally the action potential. So as the channels are opening and closing, no stimulus, no change is going to cause another action potential to occur because only one can occur in this time frame. And granted, this is over milliseconds, so these resting potentials or refractory periods are quite short. But then we have one other area, and this is called, or I guess it'd be here, we'll call this the relative refractory period. So in this hyperpolarization area, right, we are farther away from our threshold. When we're farther away from the threshold, it's harder to get another action potential. So because during this hyperpolarization, in order to cause another action potential, the cell needs greater stimulus. So during this refractory period, this relative refractory period, the same stimulus cannot cause a second action potential. However, if there's an increase in the strength of the stimulus, it will cause another action potential. It can get a faster action potential. Other than that, though, we covered the different phases of action potentials and what happens in the channels, and then we talked about graded potential and action potential, right? Here's our graded, here's our action. Graded is beneath, the action is above the threshold, and then we talked about capacitance and length constant, as well as how myelin affects those things. Thank you so much for watching. I'm sorry this video is so long.